Here is a number, 0.7, and here is a claim. The probability of rain tomorrow is 0.7. Everyone nods along. But what precisely does that number mean? It is not obvious. Tomorrow happens exactly once. It will either rain or it will not. So what is being measured, and by what? Before any axiom, before a single formula, this course owes you an answer. The oldest answer is the simplest. Count the outcomes you want, divide by the total number of outcomes, and that is the probability. A die has 6 faces, 3 of them are even, so the probability of rolling an even number is 3/6. It is clean, and it built the subject. Cardano, Pascal, and Fermat were all essentially counting, but it smuggles in an assumption that the outcomes are equally likely. Load the die, and the counting still returns 3/6, and the answer is now simply wrong. Worse, the assumption is circular. Equally likely means equal probability, so this definition of probability quietly uses the word probability inside itself. And it has nothing whatever to say about rain tomorrow, which has no symmetric faces to count. The second answer throws out symmetry and replaces it with repetition. Flip a coin many times and watch the running fraction of heads. It lurches about at first, then settles down. Probability is whatever that fraction converges to in the long run. This is a genuinely different idea, and it is the one most working scientists carry around. It needs no symmetry at all, only an experiment you can repeat. Load the die as heavily as you like, roll it 10 million times, and the frequencies will tell you the truth about it. But look at the cost. Probability is now a property of a repeatable experiment, defined by a limit you can never actually reach. And it still says nothing about rain tomorrow, because tomorrow is not repeatable. There is no long run. The third answer gives up on the world and turns to look at you. A probability is a degree of belief, how strongly you expect something, made precise by the bets you would be willing to accept. If you would pay 70 cents for a contract that pays $1 if it rains, then your probability of rain is 0.7. And this works for anything: a horse race, an election, a defendant's guilt, a theory being true, one-off events included. The obvious objection is that it is personal. Two reasonable people can hold different beliefs about the same event, but it is not arbitrary. If your degrees of belief break the rules, someone can offer you a collection of bets that you accept one by one, and that lose you money collectively, whatever happens. That is called a Dutch book, and avoiding it forces your beliefs into precisely the shape that probability requires. Now the striking part: 3 very different answers: counting, frequency, belief, and all 3 obey the same 3 rules. A probability is never negative. Something must happen, so the total is 1. And for outcomes that cannot occur together, probabilities add. That is what Kolmogorov did in 1933. He stopped asking what probability is and wrote down instead how it behaves. The axioms are deliberately silent about meaning, and that silence is exactly why they work for everybody. So the argument about interpretation never touches the arithmetic. A frequentist and a Bayesian compute conditional probabilities identically. What they disagree about is which things may be assigned a probability at all, and that argument surfaces much later, in statistical inference. The mathematics ahead of you is common ground. Probability: 3 ways. A ratio of equally likely cases, a long-run frequency, or a coherent degree of belief. Each one of them fails somewhere the other 2 do not. What they share is their behavior: never negative, totaling 1, and additive over outcomes that cannot happen together. That shared behavior is the entire foundation of the subject. Next, the vocabulary those rules are written in: sample spaces, events, and the 3 axioms in full.